get started. So first thing I want to announce that there's a homework 3. It's due in a week. It's pretty easy, except it has some subtleties that you need to understand. So let me go over the problems real quick. The first one is the band structure for gallium. So you guys have seen this in the book, but this is actually one that was calculated with DFT. So one of the important things to know about DFT is that it gets things wrong, right? It's really good at some things, but it's not really good at everything. So here, I put in the value of the band gap according to an experimental measurement. Somebody measured gallium arsenide and they found that it's around 1.4. Can anybody tell me what you think the band gap is here? Sorry? Yeah, this band gap right here. How much is it? Exactly. So you see that this is 1.42 experiment. This is not 1.42. So anyways, that is wrong. But what I want you to do is figure out this band gap, then the effective masses of the holes and the electrons. So there's two things here that are important, right? How do you get the band gap? Well, you measure the distance from here to here, and you could use a ruler to get this and put a scale bar or something like that. Now, using a ruler is old school, right? Anybody born after 1970, I don't think knows how to use a ruler anymore, right? To like make things bigger and stuff. Like we used to do all these tricks to make pictures bigger. You would see it now you see them in architect offices, like this setups of how to transport a measurement that is tiny into a bigger one, things like that. What you do now is that you have a way to measure things with the computer. So there's a very nice set of softwares. Like you put in this picture, you take a picture of your screen, you put it in there, and you actually can get data out. DG plotters, a bunch of them. So what you would do is that you give it the scale, right? So for instance, he would ask you, where is 0? You could say, this is 0, right? So this is 0 right here, because this guy is 0. And now what you need to do is point at this line right here, point at this line right here, like if you zoom in, right? There's the data here, and you can get digi points out of it, digitally what the points are. Does that make sense? All right, so once you have that, you can do the following. You can graph 1, 2, 3 points in this curve right here. You can graph 1, 2, 3 points in this curve right here, and you can graph 3 points in this curve right here, and figure out what is, as a function of whatever this is on the bottom, right, in the x-axis, what is the energy? So here's a question for everybody. Before you answer it, okay, just think about it. What is this measurement on the bottom? All right, anybody knows what is this thing in the bottom? What is the x-axis? Exactly. So these are the coordinates in k-space. So what's in k-space is kx, ky, kc, right? So I have this one right here. So here, catch. You're gonna make that. That's one of the problems that you have to do. You see it right here? So gamma is the 0, 0, 0 position. And then there's two directions that are there that are very important. One is L, right here. So let's go back to the band structure, thinking about that figure, right? So if we grab the band structure, Okay, over here. This is L. So this guy is 0, 0, 0, and I'm giving you the value right here. 0, 0, 0. And okay, here, those gamma is at 0, 0, 0 in momentum space, right? And L, this L, is in the direction of the reciprocal vectors pi I, pi over A, pi over A, pi over A. Does that make sense? So let's say that we had a projection in this is Kx, this is chi y. Where 0, 0, let's say is here. So this is where my gamma is, right? So now this L point is located at pi over A and pi over A. So maybe here. And this is pi over A, pi over A, pi over A. I'm missing the other one, right? So there's another direction that is coming out of you. So this is a two-dimensional projection. So now you have that this vector is at pi A, pi A, pi A. So there's a distance that goes from here to here. And those are your points in this direction. This is not a, this is how the energy goes when you go across this line. Does that make sense? Yes? No? So when you go across that line from 0, 0, 0 to pi A, pi A, pi A, you get this line. And this is telling you over here, this line is telling you how this energy goes when it goes from 0, 0, 0 in that direction, 0, 0, 0 in that direction. So when you're digitizing this data, right, you know that this is 0, 0, 0, 0 because it's 0 in energy and 0 in this distance traveled. And then going from here to here, right, you're gonna go from 0, 0, 0. How much distance did you cover? Well, distance is equal to the square, right, of one number plus the other number plus the other number. So this distance, right, is pi over A minus 0, right, because it started at 0. Pi over A minus 0, pi over A minus 0. So that's that whole distance from here to here. So now when you click on the points, data points to get this distance right here, the position of this points is going to give you like 0, 0. Let's say here is negative 0.1. Around here is negative 0.1. And then because you know what this number all the way over here is, this is in the x-axis is whatever this number comes out to be. Now you know where your data points align with. If you pick this point that is 0.1, negative 0.1 in energy, and maybe it's like something in the momentum space. Okay? Same thing over here. This is K, the K point. This is a these are very symmetric points. Who has my little Brillouin on? All right, try it to me. All right, so I said this is the L point. So this is one of the L points. But actually this one, this one, this one, this one, all of these are L points. That's the symmetry of this monster, right? Super symmetric. There's not just one, there's a bunch of them. There's only one gamma, but there's a bunch of L's. But it's the same thing, it doesn't matter. By symmetry, a rotation doesn't do anything. So if you look at the K point, the K point is at this point, right? So this is a K point, this is a K point, this is a K point, and so forth in this Brillouin zone. So one of the K points is given by 3 pi over 2a, 3 pi over 2a, 0. So then you can figure out what is the distance in this direction. Does that make sense? So once you have, as a function of energy, what these vectors, not vectors, but these numbers would correspond to, then you can write an energy as a function of k in that particular direction. And then the other one is different because this distance from here to here is not the same as the distance from here to here. And once you have that, now you can look at the formula that says what is the effective mass, right? And the effective mass had to do with, you have an energy as a function of K, and you're fitting a parabola because you're gonna take at least 3 points to do a quadratic fit. Once you do the quadratic fit, you can take the second derivative of it, which is what you need for that effective mass. So I don't know if anybody has questions at this point. This is the hardest part of the assignment, and mainly because you probably haven't done all of those steps before. Maybe you've done a few, maybe you know how to do quadratic fits. Everybody knows how to do quadratic fits of data? All right, so you just open up a website, whatever, quadratic fit, you put your 3 values, boom, it gives you the A, B, C. If you're fancy, you can figure out how to do it by hand. But there's a bunch of websites that can do it for you, Mathematica or anything like that, Python. And the digitizer is, there's a bunch of different softwares that can help you with that. They're free. Questions? No? All right, then the other questions are not hard, but if you've forgotten about them, this is something we were doing. We're gonna figure out, have a plane wave, and now you have 3 scatterers, and figure out what is the scattering cross section far away. I think we did that for 2, so I'm giving you 3. Then it's looking at the symmetries of this guy, which you can construct. And then this one is my favorite exercise in this course. So this is related to growth. How many of you don't like programming? Sorry, guys. So what you're doing is that you're gonna do a very simple model that shows how the complex behavior of growth of dendrites. So what you're doing is that you're gonna have a grid. You're gonna put in this grid, well, actually, is kind of like this. Let me come back over here, stop sharing this. Turn on the camera. All right. So the idea is as follows. Imagine that this is the grid that we're talking about, right? There's a position here. This is the X direction. This is the X direction. This is the Y direction. And for instance, there's a point right here, maybe this point right here. But this one is 100, and I forget if I call it 0 or 1. It doesn't matter, right? Let's call it 1. So let's say that there was a grid that was 100 in the x-axis, and then it goes in this direction, like that, and maybe it's like 600. It just depends on how much you want to draw with it. So the next step, the first step is that you put a point right here. So in this grid point, this one is occupied. But then you're going to bring in a guy right here at some position. And you're going to have to do the following procedure. You could do this even by hand, but I think I'm asking you to put like 1,000 particles in there. So you don't want to do it by hand. That's why it's easier to code it and do the step-by-step in the let the computer do the step-by-step. So then this guy, you're going to have a procedure, an algorithm that says, I want to figure out, I want this guy to look around itself. And if there's any particle nearby attached to it and just next to it, then it can attach to it. If not, we're going to pick, let's say 4, and between 4 numbers, 0, 1, 2, 3, 4. And that could mean that it's moving up, right, down, left, or right for you guys, right? So it looks around, it doesn't see anybody, picks a random number, boom, it says that it has to move in this direction. Does the same thing, doesn't find anybody, he moves in this direction. Does the same thing, doesn't see anybody, random number pick, moves in this direction. Looks around it, doesn't see anybody, moves in this direction. And then it's gonna do this, maybe like this. And then all of a sudden, it gets to this point and it says like, hey, I can attach to this substrate. And then you do that again. And now you have another particle that is randomly coming in. Let's say that this one randomly comes in and is attached. It's not attached, it's here. Looks around itself, it doesn't find anything, goes here. Looks around itself, doesn't find anything, goes here. Looks around itself, doesn't find anything, goes here. Looks around everywhere, doesn't see anything. Then randomly, this direction is the direction that is traveling. It can go back on itself this way, this way, this way, this way. Then all of a sudden, it gets to this point. And now it sees that there's a neighbor down below. And then it just makes this. Now, this one is attached to this one, the green one to the red. The next one comes over and starts doing that. And you're going to throw 1,000 particles following the recipe. Yeah?
Bringing the particles in one at a time or small?
No, one at a time. Yeah. And you can think of this as a substrate. And these are particles that maybe they're from your plume from the laser inside the plasma in your, I'm blanking on the word. What's the word? Sputtering, right? Something like that. And you can see the growth in those. So those are the homework problems. So this one is one of my favorites for this class because it has to do with calculating things. Questions? So the recipe of how to do it is basically following all of this. Right, so I'm asking you for 2,000 particles. All right, so if I don't hear questions right now, I'll be happy to listen to talk to you about how to build it. You can do it with Python, you can do it with Mathematica, with whatever code you like to use. Maybe you know how to use Visual Basic in Excel. That actually would work because you can make Excel put the color in the grid. And I don't think it's too hard, but it might be hard if you never use computers. Okay. All right, so who wants to go first? Come on over. So now we're gonna do presentations. We have 2 for today. They're in downloads, right? There we go. And let me just start it. All right, so Masrur is going to tell us about solid state NMR. Here you go.
I didn't start yet, but yeah, in future we'll use it. So today I'm going to talk about solid state NMR. So first, what is NMR? So NMR is the technique to study a nuclei. So what's nuclei? We know that in atom, nucleus is inside, in the center, and electron revolves around. So in the nucleus, we have protons and neutrons, and this is called nuclei. So in this technique, we study a nuclei to assess the nature of the structure. We can come to know about the chemical structure, the 3-dimensional structure of atoms. using external magnetic field and electromagnetic radiation. So when the magnetic field is inserted to when magnetic field passes to the nuclei, nuclei can split into two energy states. One is ground state and another is excited state. And when we pass the electromagnetic radiation, the nuclei can absorb radiation and can excite from ground state to excited state. So I will explain later. So there's the basic thing of NMR. And so in solid state, NMR basically used for the solid materials by this name, that solid state. That is the powders, single crystals, and amorphous samples and tissues. So today I will focus basically on the NMR part that sound me too interesting. So what's the criteria required for NMR signal? So first requirement is that a nuclei having a spin quantum number half. So why not 0 and 1? I will explain in next slide. So is the first requirement. Second is applying external magnetic field, that this magnetic field will split the energy level to like ground state and excited state, and supply energy in form of electromagnetic radiation that will help to that the nuclei will absorb the electromagnetic radiation and it will excite from ground state to excited state. So let's discuss about the first criteria, that nuclei having spin quantum number half. So what is so there spin quantum number can be 0, 1, or half. So I want to use board. Can I switch the light? So for when both protons and neutrons are even, we get spin number 0. Like for example, like so here proton is 6, neutron is 6, and here so its spin number is 0 because we have a proton in pair and neutron is pair. So this is called in this case, when proton neutron both are even, it's called this time spin quantum number is 0. When spin quantum number will be half when, for example, here proton is 1, neutron proton is odd and neutron is even. So when we'll get odd nuclei, means the sum of proton and neutron will be odd, we'll get half because we have one proton that is not paired, is half. And we know these are fermions, so its spin is half. And for I equal to 1, like for example, so when we get both proton and neutron are odd, we get spin number 1. So if we now we can from spin quantum number we can calculate the magnetic quantum number, magnetic moment number. So the calculation is m equal to 2i plus 1. So when I equal to 0, we get m equal to 1. Here we get m equal to 2. Here we get m equal to 3. Now, so if we applied magnetic field here, we won't get any another state. It will show us only one state. But when we will, if m equal to 2 means if we apply magnetic field, then it can split into two energy state. Like so. And if we apply magnetic field, then we get 3 energy state. So is as here is only one state, so we cannot use in NMR because we need 2 energy state. Here it's perfect. we can use it at ground state, energy state, and the plus up minus up means like it basically just a compression is just basically the difference is basically the rotation. Like if proton is rotating this way, when it will be excited, then it will be rotated that way. But here minus 1, 1, 0. So we cannot get something like this here. So only one possibility to use NMR only when the I equal to half. So why I is required. So only the odd nuclei or the spin quantum number with half can we can get the NMR spectroscopy. So now how NMR spectroscopy works. So we already told that. When no external magnetic field, we have only one spin. When we applied a magnetic field, it can turn into two state. One is ground state and one is excited state. So first proton, the nuclei stay in the ground state. When we supply the electromagnetic radiation, it absorbs it, and we have to give the particular electromagnetic radiation that will create the resonance. We say here nuclear magnetic resonance. So when we give the particular energy, certain amount of energy, then it will absorb it and give us the absorption spectra. So typically in this level, it has to be used the radio wave. So that matches the difference. So it's the basic principle of how NMR works. So now I want to show the energy calculation like we already. So what's the energy difference? So what's the energy we needed as electromagnetic radiation? So here we got two states. So the energy should be like mu is the magnetic moment and B is the magnetic field we inserted, and not. So mu half can be written as the gamma is the gyromagnetic ratio, and sorry, is B naught minus plus 1/4 pi gamma is B naught 1/2 pi gamma is B naught. So that's the energy we needed to supply, and from del E we get the frequency difference. That's the main issue for our NMR. We can cancel the H both sides. So that is called the Larmor frequency or precision frequency. That is this one. So basically we compared the Larmor frequency or precision frequency in our NMR spectroscopy, and from here we analyzed about the atomic structure. So now the question is how signals are measured in NMR, the characterization technique here. So we can start with a easy one. So here is hydrogen, methane. So hydrogen, for example, we can consider this hydrogen. It is attached to carbon that is connected to other 3 hydrogen. Also, we can consider this hydrogen, it is attached to carbon that is connected to another 3 hydrogen. So here it seems that all hydrogens are in same condition. Same, they are the neighbor and everything are same here. So it will give us only one peak. So before going that, here ppm is called the parts per million. So it's the it represents here the frequency difference, the Larmor frequency difference. Larmor frequency here we got it is like so how we so from ppm if we so we also have a 0 means we use the standard here. Please. Do you want to ask a question?
No. So essentially, this per million gives you a sort of a relative quantity.
Exactly. That's the yeah. So that yeah. So and so here and we get the and from so the peak is here. We get the chemical shift between with this difference represent the chemical shift. So now explaining chemical shift. Explain. So why this chemical shift happens? So this is because of shielding and deshielding effect. So like so when magnetic field is applied, also there are electrons. So like in nucleus, the magnetic field is applied this way, but the electrons they create also a magnetic field this way. So though we are giving the B naught, the applied constant applied magnetic field, but it is effective. So if I consider this B naught, and it's called sigma B naught. So the B external get. So the atom to atom it differs. For example, we can come here, right? We have ethyl bromide. So we'll explain how we will try to explain how we will get here. We are getting 2 peaks. So the question is why we are getting 2 peaks here. So so before when I talked on methane, we said that here hydrogens are all in same environment. That's why we got one signal. Now, like this hydrogen, it is connected to C. That C is connected to 2H and another C. This H is connected to C. That is connected to another 2H and 1C. So these hydrogens are in same condition. Their neighbors are same. So so this will give us 1 peak. Though it is saying it is not 1, but I will explain why the slight differences are. But let's consider this is a 1. And another these hydrogens. Oh, by the way, why I am saying again and again that hydrogen will give us the peak. I think time is. Will you give me some more time? Okay, so we are always saying that hydrogen is giving the NMR signal. Why not carbon? Can you tell me anyone why carbon cannot give signal? Why? Because we mentioned that we need the odd nuclei or I equal to half. So carbon is not half, either 0 or 1. Yeah. So here, so let's so for these hydrogens we got 1 peak. For these hydrogens, look here, hydrogens is connected to C. That is connected to another bromide. This other hydrogens was not in condition. So this hydrogen is in same. Their neighbors are same. They're same condition. So these both will give us this peak. Let's consider this 1 peak. So we are getting 2 signals. Now I'll just say why the difference we see here. Like there is three signals. Those are very near, right? Here are 4 signals. Those are very near. The difference is happening because of J coupling or spin-spin coupling. So so it's very interesting about, but I will not explain it now. If anyone asks question, then I can reply. That's just I am just mentioning now. The rule is that so as hydrogens, these if I consider this hydrogen alpha, these are beta. So they are the neighbor hydrogens and they affect these hydrogens. And this causes the spin interaction. And for this, so here the rule is n+1 rule. So these hydrogens are connected with 2 hydrogen. So we will get 3 peaks here. That what we got here, 3 peaks. And also these 2 hydrogens are connected with these 3 hydrogens. So in the n+1 rule tells us that here we got the 4 peaks. And so that's all. Thank you.
Could you go back and sort of explain that beside the J coupling?
Yeah, I didn't fulfill it. Yeah. So if you ask question, then I can go in deep. But yeah, ask me question. Yeah. So what's your question?
No. You mentioned that, yeah, you explain that a little bit more.
Yeah, I can, but I need around 3 to 4 minutes to explain. So should I go?
Yeah, I was asking like how the spin coupling like is leading to the n+1.
Yeah, like there is 4 peaks, there is 3 peaks. Yeah, but how you can ask that how n+1 rule came? Yeah. Okay, so like so the J coupling is called, I think maybe we read it in quantum mechanics 1 or 2, J coupling. So like for example, we are considering the alpha hydrogens, like, and there is 2 neighbor hydrogen. So like these alpha hydrogens are in this magnetic field, this way. Magnetic field direction is this way. But there is 2 hydrogens, their magnetic field would be either the one direction or opposite direction. Like we can get the possibilities. This is one. So this hydrogen, another is this hydrogen. There is 2 hydrogens, right? So suppose, so there is a possibility, right? Both are same direction. Possibility opposite direction or same direction. And yeah, so both are same direction first. Second is first one is plus, one is negative, another is positive. This one is down. So these 3, the spins of these hydrogens, the combination of the spins of the hydrogens can affect the neighbors. Like that's why we are getting. Yeah, triplets. Yeah, triplet. Yeah. Yeah, 3 triplets. Yeah. So there is no singlet here because the hydrogens are like all these hydrogens here have neighbor, right? So these hydrogens have 2 neighbors and these hydrogens have 3 neighbors. So there is no singlet here. Sorry.
So you got the up, down, minus, down, up, and you got the up, down, plus, down, up.
So we have 2 up, like both are up, both are down, 1 up, 1 down.
So is this a superposition?
So like, yeah, so here it will affect, like middle one is this one, right? The middle one is this one, right? And this one is the another one, and there's another one. So same way, we should explain the how why are you getting 4, or it's okay. I'll go for the why it's 4. The these ones. How are you getting 4 signals here? Should I go to explain or? Okay, so now for these beta electrons, we have 3 hydrogen. So we have options. So what could be the possibilities? One is both are same directions. One is all at the. One possibility is one possibility is two is same plus direction, one is negative direction, and one is right. So there are four possibilities. So here we are getting like so these are two, means this one and this one, and these are the two, means this one and this one. So did you got the answer? So anyone, another question, please?
When they have these like different spins,
Spin, yeah.
then we get the highest spin, I mean the bigger spin.
Bigger peak, yeah, is the superposition, yeah. So both are applying here, right? So I mean that like this one are the same actually. So anyone, any question?
You mentioned the influence of the carbon in there, right?
Yeah.
So when you put in the NMR,
Mhm.
you put in what isotope you're looking for.
Yeah, also carbon isotope can be used, yeah.
Right. So if you have the proton NMR,
Mm-hmm.
which is what you're showing here, right?
Yeah.
But you can also get like another element.
Yeah,
So
yeah.
what is it that we're changing, you know?
I think so. I don't exactly, but I think is it maybe the like if I use the like nitrogen NMR, is there the fluorine NMR? Then I think maybe these elements have to be in the compound. Is it or
Right. So it has to do with the compound that you're looking for. Right?
exactly?
So have it here, right? What would change if you have another, if you're trying to excite another nucleus?
Sorry.
What would you change if you're trying to excite another nucleus? So you have it set up so that it excites protons.
Mhm.
What would you change if you want to excite nitrogen 13?
Definitely, I think it should be a magnetic field. Not magnetic field. Larmor frequency, exactly. So and Larmor frequency depends on the magnetic field here. Yeah. So yeah.
Right here, you're looking for protons to choose this magnetic field that is exciting.
Yeah. So different. Yeah.
If you're going for carbon, you have to change.
Yeah. So exactly.
For silicon, when you, like you said, you cannot be carbon 12, that can be carbon
13.
exactly.
Yeah.
You cannot be nitrogen 14 because that was 2 ox.
2 odds exactly. We have to have the odd nuclei.
Right. So if you go with nitrogen 15, you can have
Then it works.
7
Mhm.
and even 8.
Yeah.
Is that clear?
This is just a method of factorization to identify the material, right?
Sorry.
The material structure of the.
Yeah. So from this analysis, we can get the structures, atomic structures, the chemical structures. We can explain.
Yeah, so I mean, well, I would say that there is like a constraint that we cannot use it for every material.
Yeah,
Just
that-
a particular type of material.
Yeah, that is, you have to maintain the I equal to 0. Like you have to have the odd nucleus. That's the requirement.
All right, do we have more questions? Yep. All right, cool. Let's end this order then. Mind giving him the microphones? Hear about AFM. And you're telling us about atomic force microscopy. Have you done experiments with that? Have you used it?
So I briefly worked with Dr. Myers.
Right.
And I helped set up the microscope. Didn't really get to run on any real samples though.
Because he wasn't working. Right?
He wasn't really active yet. So, oh, I don't know what I hit. Well, I'm talking about atomic force microscopy. It's a characterization technique. It's widely used in condensed matter research. What it does is it creates a topographical map of a material, whatever you're looking at. There are 3 primary modes that it operates in, and I'll be talking a little bit about each of those modes. It's pretty versatile. You can use it on a range of different materials. It doesn't require any conductive materials like STM or anything like that. And what you get is about a nanoscale map of a surface. It was developed by Binning, Quate, and Gerber in 1986. Binning was the inventor of STM as well around the same time, and he won a Nobel Prize for that same year. So what it does is I'll show you some images in a second, but there we have a cantilever, which is basically like a diving board, and we've got a needle hanging off the tip of that, and the top of this cantilever is reflective, and we shine. Let me see eraser at. So here we have the cantilever and it's fixed. The top of this is reflective and we've got our needle coming off the end of it. And then what we do is we shine a laser down onto this reflective surface and this gets reflected to a photo sensor that can, when we run this along a surface, the surface will make the cantilever deflect and thus change the angle of this laser. And we can use a computer control software to determine how much is deflecting and what the surface looks like. And there's a couple different techniques what they do there. Here, there's a better diagram of what's going on there. The geometry of our tip can actually affect the resolution of what we're looking at. So as you can see here, this fatter tip, it can't really define these sharp points very well. So you're limited there. This here, I'll get into these different modes, but essentially, depending on how far away we are from our surface, this is our tip surface distance. So here's the surface of our sample. This is our tip surface distance here. And as we bring it in closer, you can see we have from nothing into a negative interaction. And as we get even closer, when it actually makes contact with the surface, we'll get a positive reaction. So the first mode I'm going to talk about is contact mode. And essentially, the tip is in contact with our surface, as the name implies. What the surface of our sample is on a piezoelectric stack, which basically allows us to move it XYZ really fine. We try to keep this cantilever at a constant deflection. So whenever it hits say a bump in the surface, it's going to deflect. And that tells our software, hey, we need to move away from the tip to bring that deflection back to constant. And it uses that amount of change to like say, hey, this is some geometry on our surface. It offers a pretty good resolution in contact mode, but you do have to run it slower because you do risk damaging the material you're looking at because you are rubbing a fine needle across it, and you could, depending on the surface or whatever you're growing, it could. Do you have a question, Cosmo?
Yeah, how fine a size is this tip usually? Are we talking like on micron scale or?
I think, yeah, micron scale. I could be, I think I don't know about that one. Okay. Another big mode is a non-contact mode. And what they do in this situation is we oscillate our cantilever at a resonant frequency. And by bringing it off the surface by somewhere in the order of 0.2 to 10 microns, as it hits a surface detail, it will pull it out of that resonant frequency just based on van der Waals forces. It'll shift the oscillation out of that frequency. And again, we pull it away until it hits its resonant frequency, or we drive it some more until it hits its resonant frequency. And that is interpreted by the computer. You do get a little bit lower of a resolution in some cases, and in some cases even better. I'm not sure how those two situations work, but you are allowed to move a little bit faster in this situation just because you're not in contact with the surface and you're not worried about damaging your material. There's also another variation on this called tapping mode, where it's resonating, but we bring it in a little bit closer and we allow it to tap the surface every so often. And it's kind of a hybrid between the two. I believe tapping mode gets a really good resolution compared to just regular contact or non-contact. There are a lot of variations on these methods, but they all rely on the same core ideas between those three modes. Let's see. Again, it's really versatile. It doesn't matter. With insulators and conductors, that's why it's so widely popular within the condensed matter community. And it's not really temperature sensitive. It can be sensitive to humidity sometimes, but that's usually not an issue. One of the biggest things is that it needs to be vibrationally isolated. You have to suspend it in a system or have some kind of active vibration isolation. But other than that, that's pretty much microscopy for. Any questions?
So if you go back to your third slide, there's a picture right there, right?
This one?
No, the other one. This one, that one.
Yeah.
So this one shows the grafting lattice.
Yes.
So that gives you the kind of like the resolution of this guy. It's there. I don't know. Look those guys. Do you know how they took this picture or who took it?
I have the link to the people who took it, but I didn't look into what method they were using. I should have put that on here. That would have been a good idea.
So that shows you that you can have atomic resolution under perfect conditions.
Do you know why they choose the color orange? Because like a lot of AFM images are orange, but
Yeah, I know. I think that because STMers use the scale, and this guy's one of the differentiate from STMers because they're not using that. And I think that maybe their software is really the thing that manipulates all the data and makes it look like this topography maps.
Cosmo, do you have another question or?
Yeah, generally speaking, when you're selecting the variations of the different contact methodologies for this cantilever mechanism, what sort of factors usually go into one getting selected over the other, whether it be contact, non-contact, or tapping?
I think it takes, you have to have some expectation of what your surface is going to look like. And you have to know what are the chemical and like magnetic properties of your surface. because those can contribute to the forces. But you can always use trial and error, I think is often used. But you do have to be careful if you're going to use something like contact mode and you go too fast, you could ruin a sample, and you can even ruin the tips. And those tips usually aren't super cheap.
Right, there are $400. Any other questions? All right. so that's it. Very- And at this point,
So we're back in magnetism. No, sorry, in conductivity. But now we're going to look at a magnetic field, a system with a magnetic field. So we have covered AC conductivity, we have covered DC conductivity. Now let's look at conductivity in the presence of a magnetic field. You guys remember all of the qualities of the Drude theory, right? The rules for Drude theory. What we want to have in it. So this is similar to the theory of the gases, right? And what I want to cover for you guys is the Hall effect and magnetoresistance. How many of you know about the Hall effect? Who's heard of it? Cosmo? What is it?
But I do know that there are a number of control systems that are using sensors in order to gauge granularity for fine-tuned joysticks and electric control systems.
So, anybody else knows who Hall was? Sorry? Yep. So the Hall effect is useful because it tells you what kind of charge you have exactly. If you have electrons, it gives you the negative charge by convention. Let's say you had ions that are conducting in your system. You could have ions, right? Then it would give you the positive Hall effect coefficient. If you have holes as the conductors in your system, it will give you that they're positive too. So that's the probe that we use nowadays. So imagine it's 1879. What kind of physics would you be learning? What would be the state of the art? Everybody's talking about it. Maxwell equations, right? Maxwell's book just came out, and Hall is a scientist, American scientist. He's actually probably the first in many years scientist that gets an international reputation. So you guys know about Franklin. Franklin had an international reputation, right? Ben Franklin, one of the founding members, writers of the Constitution, all of that, he was also into doing science and playing with kites and stuff. So Hall is one of the few people from the United States, because back then the science was done only in France and England and places like that, and they wouldn't look this way, right? So Hall is reading Maxwell's book, and then he spots something that he thinks is wrong. And this is what he was thinking about. There was a force. So let's say that you have a wire. And this is like a wire, a cross section of the wire. And then inside of the wire, there's electrons, right? So here are electrons. And they're going in this direction because there's a current of electrons flowing right there. So the question was the following. If you put this, a current carrying wire in a magnetic field, who's gonna field? So you have a current carrying wire put in B field. Who feels the force? The wire or the charges? You're saying charge? Who would say, who says wire? Anybody here? Everybody says charges? So Maxwell, if he was sitting here, would say that you're wrong, that it is the wire. But he's wrong, actually, because it would be the charges, right? It's not the wire, it's the charges that feel that force. So this is what Hall was thinking, and he assumed that it was the charges only that would be feeling this magnetic force. He assumed that Maxwell was wrong, and he wanted to prove that Maxwell was wrong. So this is what he does his PhD dissertation on, proving that Maxwell was wrong. Imagine how brave he was. So what kind of experiment did he do? He actually grew samples, little tiny wires, little tiny films of gold foils, and put them under magnetic field. And he was trying to measure the resistance change as he was applying magnetic field. Why? Because if you have a magnetic field, right? So let's say that there's a magnetic field going in this direction. What would happen to the charges? They're moving in that direction, right? And then there's a magnetic field up. Right. But then there's the negative of the charge, right? So we would see that there's a deflection. So which way is this deflection going? Let's get this right. Because of the negative charges, the deflection is in that direction, right? So he assumed the following, because the charges are being magnetically influenced, he wanted to see, he assumed that all of the charges would go to this end of the wire because of the magnetic field. They're moving in that direction. The magnetic field starts pushing things in that direction. And he said, if I'm right, the charge is gonna pile up on one of the sides of the wire rather than the other. And he's gonna be able to measure a change in the resistance of the system. Does that make sense? So that's the experiment he was after. He actually tried it. And he couldn't measure it because he didn't have the precision. I mean, it's 1879, right? There's no precision measurement. He didn't have a digital voltmeter back then. So this is something that is actually because he couldn't measure it. Then he thought the magnetic field is trying to deflect the current, but it's not strong enough to deflect it. He's just stressing the current, but he's not able to deflect it. He didn't have a strong enough magnetic field. He couldn't get the magnetic field. I mean, again, it's 1879. He probably couldn't get the magnetic field necessary to do this change to deflect them. He was only stressing them. So B field was not as strong enough to deflect, but he could measure the stress in the current. So this current, the stressing, is what we call the Hall effect. So he was after the magnetoresistance, but he didn't have enough magnetic field in there. He didn't have the sensitivity to get the current to change completely. What he did have was the ability to measure voltage across, and that's how he gets that there's a stress happening on the system. So let's talk about this part then. So we're going to experience a Lorentz force if we were an electron in a magnetic field, right? So this Lorentz force is given to us by the speed of light on the bottom, the charge on the top with the negative in it. And then we have that this is the cross product between the velocity of the charge and this magnetic field. So we have this is the Lorentz force that is experienced. And let me make sure that I get things right. All right. So the geometry correctly. So it was a thin film. Imagine that this is a thin film. What he did first is, let's say this was the X direction, and there's actually an electric field that goes in the X direction. Okay? So that's the first thing about the setup. There's an electric field in that direction applied. So the current is flowing in, if it's electrons, in this direction, right? So we're gonna have electrons here, and they're moving with this velocity. And then there's gonna be a magnetic field. It's in the C direction. Like that. So if we go with negative E, B cross H, H is on the top, this is the direction, but then you have the negative, you actually would have that there's a force going in this direction, right? And this would be the negative E, B cross H force. Questions? So what is the electric field that is happening at this point? How many electric fields do we have? Amen? We have charges moving in this direction, right? Right. This electric field is the one moving the charges. And then the charges experience this force in this direction. So what's happening with those charges moving in that direction? Nikita, what do you think happens there? So the electrons that are going in this direction get pushed in this direction, right? So now you end up with negative charges here on this end of your wire. And then there's a positive over here because there's charge on this side, right? So that means that because of these two forces, because of this charge difference, you also have this electric field in the y direction. Does that make sense? So let me make this bigger. Electric field in the y direction. So you have that the piling, there's electrons. The electrons are moving in this direction, but then they're getting deflected by the magnetic field, and then they pile up on this end versus this end. So this side is more positive charge, this side is more negative charge. Positive to negative, there's an electric field in this direction. Sorry, is it in that direction or the opposite?
Because the electrons are moving this way, so the field should be the opposite direction.
Yep, it should go in the opposite direction. You're right. Right. So there should be a field in that direction. Right? Negative to positive. There's an electric field in the y direction. So this is the y direction going up. Does that make sense now? The geometry, the setup? Yeah? All right. So the piling of electrons generates an electric field in the y direction. And what happens then is that there's a force pushing the electrons in this direction, right? This guy. So now it makes sense. There's this force pushing the electrons in that direction. But then you're creating an imbalance that generates an electric field that points in that direction, and it cancels the other force. So you have a force pointing in this direction, magnetic force. Then you have a force pointing in this direction from the electric field. And they're opposite each other, so they cancel out. So that's why he couldn't see a deflection, right? Because the magnetic field was being canceled by the accumulation of charge here. So there was no real deflection. It was actually just creating this whole electric field that is pushing things in the opposite direction. So electrons are pushed pile up on the negative y-axis, negative y surface. This pile up generates new electric field in y direction until the two forces cancel out. So they have reached an equilibrium. And when the two forces are canceling up each other, there's no deflection of the current. They're just there. But if you take your voltmeter, you would be able to measure that there's an imbalance between this end and this end. So imagine that you're back in your electronics lab, having a lot of fun, burning all the diodes, right? Then you would be able to take this measurement under a big enough magnetic field. Questions at this point? All right, so then we can look at so in this case, we can measure the current versus applied E field And if we do that, we will be looking at this quantity as a function of the magnetic field, the field in the x direction divided by the current in the x direction. So this one is what we call the magnetoresistance. Again, he couldn't generate a large enough magnetic field at the time to actually measure this change in the system. Now, you on your labs would be able to do that because we have way better things to measure current flow, right? Changes could be measured. And then the other thing is that we can also measure the ratio between the transverse E field and current flow. And this one has a dependence on the magnetic field. So we have that this thing is called the Hall resistance. It's not resistivity because at this point it's just measuring from the sample, right? So it's the resistance. It has the geometry of the sample. And it would be that electric field in the y direction divided by the current in the x direction and multiply by the magnetic field that you're applying. So the resistance that you measure would be positive. This is called the Hall coefficient right here. First measured by Hall. And this Hall coefficient is going to be either positive or negative. For instance, if you have positive carriers as your charge carriers, then the alignment between this applied electric field, this generated electric field and the current gives you a positive value. If you have negative charge carriers, then this applied electric field is going to be pointing in the opposite direction, and you would get the sign of what kind of carriers you have. Let's say you make something in the lab and you don't know if it's carriers are electrons or holes. This measurement will give you exactly what they are. And it's really easy to make, right? You just need a voltmeter and a battery to generate the voltage. Questions? No? So during these measurements, Hall was able to prove that Maxwell was wrong and the charges are the ones that move under magnetic field. It's not the foil that would move. That's what Maxwell was thinking was wrong and what was wrong about Maxwell's idea. He thought that it wasn't the charges that were moving, that it was actually the material that would move. You also have to remember that back in those days, nobody even knew if electrons really existed, right? They could be imaginary things that we didn't know that they're really there. All right, let me stop right there. And you have a homework to do. This guy, you don't need to turn it into me. You can keep it as a souvenir. But you do need to make it so that you can figure out what are the cool symmetries that you can see here. And if you have any questions about the homework, like how do I get the, how do I make it so that I can capture the points, come and see me in my office, okay?